Good morning, students. In this video, I'm going to discuss Bohr model of atom. Previously, Rutherford and previous to Rutherford, Thomson gave out some idea about how the atom should be. Atoms are spherical. Rutherford, after experiment, he figured out that most of the space in an atom is empty. So next comes Bohr, and his model, proposed model, was the most accepted and the most widely used model considering an atom. So in the next slide we can see here these are some of the postulates given by Niels Bohr, and he put forward his model in the year 1913. This is the most widely used atomic model to describe the atomic structure of element, and Niels Bohr, he put forwarded his model based on the observations of Planck's. He put forwarded this atomic model based on Planck's quantum theory. Now here you can see in this diagram, at the center nucleus is present and there are certain fixed orbits, and electron is here in one of the orbit, and this electron is revolving around the nucleus. Now his first postulate, he said that electrons inside atoms are placed in discrete orbits called stationary orbits. Electrons can jump to higher levels by absorbing energy and move to lower energy levels by losing or emitting its energy. As long as the electron stays in its own stationary orbit, there will be no absorption or emission of energy. Electrons revolve around the nucleus in those stationary orbits only. Okay, so Bohr has coined these orbits as stationary states. He named these certain orbits as stationary states. Another point, he said that the energy of these stationary orbits are quantized. Now if the energy of these stationary orbits are quantized, now I want you to emphasize on this term quantized. Okay, by saying quantized, it means these stationary states, they cannot have any arbitrary value. There are certain fixed values assigned to the orbits. And that's why he said that the energy of stationary orbits is quantized. This means they have a fixed value. An electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. That is why only certain fixed orbits are allowed. So one by one we are going to discuss all these points, and the things will be ultimately very clear to everyone. The first point, you see, the electron in the hydrogen atom can move around the nucleus in a circular path of fixed radius and energy. As we can see in the previous slide, that if this is our nucleus and the electrons are revolving around the nucleus in certain fixed orbits. Okay, and Bohr said that these fixed states he named these orbits as stationary states, and these stationary states has a certain fixed value of energy. If their energy is fixed, then definitely these orbits are also unique, and if the orbits are unique, then definitely their radius will also be unique. So that's why it can be said that nucleus in a circular path of fixed radius and energy. This means electron can revolve around the nucleus in certain fixed path which have fixed radius and fixed energy. And Bohr said these paths to be as orbits or stationary states or allowed energy states. Stationary states or allowed energy states. The most important property associated with electron is the energy of its stationary state, and it is given by the expression this one. En equals to minus 2 pi square m e to the power 4 z square divided by n square by h square. Now you see, there is a detailed explanation how this energy expression came out, but things would get complicated, and we will study these things in higher classes. Okay, so that's why I'm omitting all these things, and this is the simple formula. You can remember this. Okay, so the energy value is given as minus 2 pi square m e to the power 4 z square n square by h square. Okay, where m is considered as mass of electron. Okay, z is the atomic number of an atom. Here in this theory, Bohr was explaining hydrogen atom. So for hydrogen atom, the z value is 1 because the atomic number of hydrogen is 1. And what is n? N gives us the number of shell, the number of orbit. N gives us a number of orbit. Say for example, if this is our nucleus, this is our first orbit, and this one is second orbit, this one is our third orbit. Okay, so for first orbit, n value is 1. For second orbit, n equals to 2, and for third orbit, n equals to 3. So basically, from n, we can know that where the electron is placed, in which orbit the electron is placed, whether it is in first orbit or second orbit or in the third orbit. Okay, because as I said earlier, the energy values of all these fixed orbits are fixed. They have a fixed value. Now, if the energy shell changes, then definitely its energy will also change. Okay, so the n value will go on continuously, and the value of n can be 1, 2, 3, 4 like this. Okay, the far you go from nucleus, the n value increases. Now you see, out of all these values, except z and n, all these values are constant. Except n and z, all these values are constant. Okay, so by putting all these values for constants, we have finally gathered out this expression. Okay, so in short, if you cannot remember this expression, you can also remember this one and this one and this one. Now what is the difference between these two? All the three are expressions. They are of energy expression only, but the difference lies in the unit. Okay, so depending upon the unit, the value of constant will go on changing. Here n signifies the number of orbit and z signifies the atomic number of the atom, about which atom we are speaking about. Okay, so if En equals to minus 21.8 into 10 to the power minus 19 joules square by n square, then the unit would be joule per atom. Okay, here in the next expression, En equals to minus 13.6 z square by n square, and the unit is electron volt per atom. Electron volt per atom. Here the value is minus 1312 z square by n square kilojoule per mole. So these are the expressions. Depending on the question asked, you have to use the values. Similarly, here you can see this is the value of radius. Radius of whom? Radius of the allowed energy states. This is the general expression. Okay, so from here we can see the whole these values are constant. Okay, so by putting all these values, we have equated all the constants as a naught, and the remaining section is n square and z, because z will change with atom and the value of n is going to change, because that's what depends on the radius. Okay, the radius of first orbit would be smaller than the radius of second orbit. Okay, now if we put all the values of the constants, here we can get this value. R equals to 0.53 n square by z angstrom. Okay, n square by z angstrom. Okay, so this is the part you have to remember. Here the radius equals to a naught n square by z, and by putting all the values we can get the radius as 0.53 n square by z angstrom. Okay, Now you see one thing, if the value of Z is 1, that means if we are speaking of hydrogen atom, then the Z value would be 1. Okay, and if we are speaking of the first orbit, this means the value for n will be n. So from here we can say that R equals to 0.53 angstrom. Okay, the value for radius is 0.53 angstrom, and this is for what? For hydrogen atom and the first orbit. Hydrogen atom, first orbit. Okay, so this value R equals to 0.53 angstrom is known as Bohr's orbit. This is also called as Bohr's orbit. Similarly, here also you can see the value for velocity is calculated here, and from here we can see the velocity of the electron is 2.18 into 10 to the power 6 Z by n meter per second. Remember, this is velocity of electron. 2.18 into 10 to the power 6 Z by n meter per second. Now you can see how fast the electron moves. Okay, its velocity is in terms of 10 to the power 6 meter per second. Okay, so these are the values. You have to remember these values, particularly the value of these constants. Okay, now we are moving to the next slide. Here you see the energy of an electron in the orbit does not change with time. The energy of these orbits, they do not change with time. However, the electron will move from a lower stationary state to higher stationary state when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. The energy change does not take place in a continuous manner. Now you see what here is trying to convey is, suppose say for example, this is an electron. Okay, now this electron, if it absorbs some amount of energy, the electron will go to the higher excited state, or we can say higher stationary states. Okay, so on absorbing energy, electron moves to higher stationary state. Now say for example, if here the electron has, first of all, it absorbed some amount of energy and it reached out to this state. Now again the electron is now present in this orbit. If the electron then loses some amount of energy, it can again come back to this energy state, or this stationary state. Okay, so from here we can conclude that whenever electron absorbs some amount of energy, it reaches to higher stationary state, and whenever electron emits some amount of energy, it comes back to the lower stationary state. Okay, so one more thing, if electron emits radiation, okay, if electron comes to the lower stationary state, in that case some amount of energy will be emitted by the electron. Now the question is, what is the quantity of that energy? You see, as I said earlier, that all the stationary states, they have certain fixed values. Okay, say for example, the value of the first orbit is x and the value of the third orbit is y. Okay, if electron needs to move from first orbit to third orbit, what is the amount of energy that will be absorbed by the electron? It must be y minus x. Okay, it must be y minus x. Okay, is this clear? Now when electron will absorb this amount of energy, then only the electron can jump from first orbit to the third orbit. Okay, similarly from the third orbit, if the electron chooses to come back to first orbit, what is the amount of energy that will released by this electron? It will be again y minus x. Okay, so this is the meaning of the sentence where it said the energy change does not take place in a continuous manner. The energy change does not take place in a continuous manner. Okay, it is not continuous, it is discrete. Okay, say for example, when you study for 1 year, okay, if you are a student of class 6th, okay, 1 year you will study and then only you will be promoted to 7th class, 7th standard. Okay, is there any pathway in between where you can be promoted from 6th standard to 6.5 standard? No, the amount of time here is fixed, and if you continue this 1 year, then only you will be promoted to 6th to 7th standard, not to 6.5 standard. Okay, is this thing clear? The values are fixed. They have certain fixed values. It cannot be like this, you passed the supplement, students, they cleared the SA1 exam and they got promoted to 6.5 class. No, it's not happen. Okay, it's not possible. So once the student studies 1 year, the fixed amount of time, then only students will be promoted to 6th standard to 7th standard. So exactly in this way, electron, they can be promoted to higher stationary state when some fixed amount of energy is absorbed, not any random value. And whenever electron jumps back to the previous state, emits some radiation, the emitted energy will also be the some fixed value. So this is the meaning of this whole paragraph. Okay, so when required amount of energy is absorbed by the electron, or energy is emitted when electron moves from higher stationary state to lower stationary state. This means the energy change does not take place in a continuous manner. It does not happen like this. This is not continuous. It has some discrete values. Now moving to next point. Here it is said that the frequency of radiation absorbed or emitted when transition occurs between two stationary states that differ in energy by delta E is given by this expression, or I can say this expression. Okay, again I'm drawing here. This is nucleus, this is one orbit, and this is your another orbit, or we can call it as stationary state. If this is nucleus, okay, now we will have a, just consider here one electron is present. Okay, now we know this stationary state has its fixed value and this stationary state has its its unique fixed value. If the electron needs to jump from this orbit to this orbit, it must absorb the amount of energy, which is the difference between this state and this state. Okay, say for example, the energy of this state is E2 and the energy of first state is E1. Okay, so the difference between the energy values of these two states is delta E, which is equals to E2 minus E1. Okay, delta E equals to E2 minus E1. Now we have to provide some amount of energy. Okay, and let us say we are providing energy in terms of light. Okay, in terms of photon. So if we are speaking of photon, then, or if we are speaking of light, okay, then light has its certain unique frequency, it has its unique wavelength. Okay, so not all radiation will excite the electron from first orbit to second orbit. Only if the frequency of the given radiation, matches with the energy difference of the first and the second orbit. Okay, only if each new amount of energy is given, then only electron will be promoted from first orbit to the second orbit. Okay, so the frequency of radiation that will be absorbed or emitted by when transition occurs from first state to second state, or from second to third, or between any two stationary states, their energy difference is given by delta E. So these two things can be related like this. Okay, delta E is energy difference between the two stationary states, and their energy difference must match with the frequency of radiation emitted or absorbed by the electron. Okay, so from here we can have another formula. So delta E equals to h nu. Nu equals to can be written as c by lambda, or we can write it as nu equals to delta E by h. And from here we can say nu is proportional to delta E. We can say it like this. Okay, because h is a constant. It is known as Planck's constant. Okay. In the next slide, let us see what this point is saying us. Here it is said that the angular momentum of an electron in a given stationary state can be expressed as an equation mvr equals to nh by 2 pi. And they are saying that an electron can move only in those orbits for which its angular momentum is integral multiple of h by 2 pi. That is why only certain fixed orbits are allowed. Now you see here, in Rutherford's experiment, Rutherford mentioned that nucleus is present at the center and the electrons are moving around the nucleus. He did not mention anything specific about orbits. And Bohr said that the electrons are moving around the nucleus, that is okay. But the electron has their fixed certain pathways. Certain fixed pathways. Now here in another point, Bohr is saying that from going from here to here, there are infinite number of orbits here. Okay, I can draw infinite number of lines. I can draw here infinite number of lines. But Bohr said that simply drawing infinite number of lines will not work. Only certain orbits are allowed for an electron to move. Only certain orbits are allowed for an electron to move. Okay, say for example, electron can move in this orbit, not in this orbit. Not in this orbit. Just for example, I'm saying here. Okay, so what did Bohr said? Bohr said that only those orbits are allowed for which they have certain fixed values of angular momentum. And if the value of angular momentum of an orbit is integral multiple of h by 2 pi. Okay, if the value for angular momentum is multiple of h by 2 pi, then only those orbits are allowed. Okay, so he said that only those orbits are allowed for which angular momentum is equals to h by 2 pi. Okay, and some integral multiple. N is any positive integer. What is this n? N is any positive integer. This means if the angular moment of first orbit, is h by 2 pi, the angular momentum of second orbit would be 2 of h by 2 pi. The angular momentum of third orbit would be thrice of h by 2 pi. Remember, 1.5 h by 2 pi is not allowed. Okay, n is the value of positive integers. Okay, so only those orbits for which their value comes out as a multiple of h by 2 pi, okay, integral multiple of h by 2 pi, only those orbits are allowed for an electron to move. Okay, and the formula for angular momentum is given as mvr. Okay, see here, what is momentum? Momentum is mass into velocity. Okay, So the mass of electron, so in case of angular momentum, we can write it as I into omega. Okay, I is moment of inertia, that is mr square, and this is known as your v by r. Okay, v is our linear velocity. So if we cancel out r and here r, so we get the formula of mvr. So this is the formula for angular momentum. This is the formula for angular momentum. Okay, so the value of angular momentum must be integral multiple of h by 2 pi, and then only those orbits are allowed. Only those certain fixed orbits are allowed. Okay, I hope up to this much every point is cleared for everyone. Thank you.